In this class, we will continue to discuss descriptive statistics by focusing on the tools we use to describe the center of a distribution and the tools we use to describe the dispersion of scores away from the center. The location of these three measures of central tendency depends on the shape of a distribution. When a distribution is symmetrical, the mean, the median, and the mode are all equal to each other and share the same point in a distribution. But in a positively skewed distribution, the mean is larger than the median, and the median is larger than the mode. In contrast, in a negatively skewed distribution, the mean is less than the median, which is in turn less than the mode. In this slide, you see a positively skewed distribution. Note that the mean has a higher value than the median, which in turn is higher than the mode. Note how the high scores in the distribution pull the mean towards them. In this slide, you see a negatively skewed distribution. Note that the mean has a lower value than the median, which in turn is lower than the mode. Before going to the next slide, see if you can answer this question. What measure of central tendency of income in the United States would you use if you wished to exaggerate how well the economy was doing? Because the distribution of income is positively skewed in the United States, the mean will give us the highest measure of central tendency and will tend to portray the economy as doing quite well. This is actually one of the reasons why the median is most widely used to describe income in the United States in economic data. The key point here is that the mean is the measure of central tendency most affected by extreme scores, because only the mean relies on the exact numerical value of each score in a distribution. For example, to return to the distribution of income in the United States, imagine we have computed the mean, median, and mode for the income in the United States, only to discover we had left out the income for Bill Gates. If his income were then added to the distribution, the mode would not change, the median would not change, but the mean would likely increase or be pulled farther to the positive extreme to accommodate this new score. Central tendency is also related to the scale of measure for a variable. The mode can be determined for any scale of measure. In a nominally scaled variable, the mode will be the category with the most participants, and in a ratio or interval scale, we can easily determine the mode by finding, for example, that most people received a score of 17 on a measure. In contrast, the median can be determined only for ordinal or greater scales of measure. We cannot find a median in a nominally scaled variable because there is no numerical relationship between the levels of the variable. Finally, the mean can be computed for variables using interval or ratio scales of measure. One of the reasons we will assume that some seemingly ordinal scales are interval in nature is to permit us to use the mean, which will also permit us to use more sophisticated statistical procedures. Let's turn our attention now to dispersion. Dispersion refers to how scores are arrayed around or vary from the center of a distribution. The simplest measure of dispersion is the range, which is the gap between the highest and lowest score. If we administered an exam to a group of students and the highest score correct was 50 and the lowest score received was 32, the range would be 18. A second measure of dispersion is a deviation, and a deviation is the gap between a test score minus the mean, or x minus m is a deviation score. As discussed in a previous slide on the mean, the sum of all the deviation scores from the mean equals 0 in any distribution. The deviation score helps to describe how scores vary from the mean, but we can't do much with it because the summation of the deviation equals 0. So to compensate, we square all the deviations and compute our most important measure of dispersion, which is called the variance. The variance in the population is computed by summing the squared deviations of all the scores and then dividing by the number of scores. Because the sample variance is not an unbiased estimate of the population variance, the sample variance is computed by dividing the sum of squares by n minus 1, or what we come to call degrees of freedom. So in a very important concept, the sample variance is comprised by the sum of squares in the numerator and the degrees of freedom in the denominator. You'll hear a lot more about the sum of squares and degrees of freedom later in the course. If you'll recall, a mean is an average, or is a sum of scores divided by the number of scores. Thus, a variance is really a type of mean. And this is because it has a sum in the numerator, the sum of squares, and the number of scores in the denominator. So it can be thought of as the mean, or the average of the sum of square deviations, or the mean of the sum of squares. Because the variance is expressed in squared units, it is often difficult to interpret. Thus, we take the square root of the variance in order to derive a more meaningful measure of the distance from the mean, and one that is more in keeping or more in line with the original scale we started with. The square root of the variance is the standard deviation. Because the variance is a mean, we can interpret the standard deviation as the mean distance score, or as the average distance scores fall from the mean of a distribution. So if we had a distribution of scores with a mean of 40 and a standard deviation of 5, we would say that on average scores could be expected to fall between 35 and 45. A special type of standard deviation is the standard error. A standard error is the standard deviation of a sampling distribution, and it is interpreted as the average distance a score derived from a sample can be expected to fall from its population value. So what does this all mean? What is a sampling distribution? Actually, a sampling distribution is a theoretical distribution of scores we would obtain if we were able to draw an infinite number of samples from the population. So let's take an example and see what this means. Let's say we administer a test to a sample of 100 individuals drawn randomly from the population. And using that data, we compute a mean score. Now let's draw another sample of 100 and once again obtain a mean, and then do it again. Draw a sample of 100 and obtain a mean, and then keep doing it 500 times, and then continue this process an infinite number of times. Each time drawing a sample of 100 people and computing a mean score. The frequency distribution of all of these means would be called the sampling distribution of the mean. And it would be the sampling distribution of the mean for a test using a sample size 100. The standard deviation of these means would be called the standard error of the mean. So the standard error is the average distance means of 100 individuals could be expected to fall from the population mean. The concept of the standard error will come in handy when we discuss other topics later in this class.